Hi everyone, I'm Marissa with the National Weather Service in El Paso, and with me today is Jason Laney from the National Weather Service in El Paso and Diane from Polk Elementary in El Paso, Texas. We are going to teach teachers how to teach the weather today and cover some weather basics that the teachers in Texas need to go over for their end of the year exam called the TEACS test. So without further ado, I will pass things over to Jason Laney, a meteorologist here. Jason?
All right, thank you very much, Marissa. We're going to let Marissa load up our slides here. Basically, I've put together about 35 slides, and to kind of let you know the background on this, we started offering this little basic presentation, very elementary, if you will, because we were talking to elementary school students. And it was a big hit, but it turned out that a lot of the teachers that were on board with the various classes said, you know, this wouldn't hurt to have a little briefer on this for us ourselves, as we're required to teach this, and the more we know about it, the better job we're going to do teaching it. And honestly, I used to teach an intro to weather and climate class at the community college level back in, about 10 years ago. I taught it for 8 years, and a lot of my students were just like you guys. They were teachers with their continuing education, but wanted to know a little bit more about weather so they would have a little more confidence. And really, more importantly than that, as you know, teaching youngsters, you can give them all sorts of facts and figures, but they know one magical word that can drive a teacher insane, and that's the word why. And a lot of times, that's what puts the teachers on the spot. So I'm going to give you guys the opportunity to ask me some whys a little later on some of the facts that I give you. So more or less kind of think of it in terms of how your students may take in some of this information and what some of the questions they may have, and maybe we'll be able to share those together. So we call this our Weather Basics. We are teaching teachers. Now, obviously, teachers already know about this stuff, but we're hoping we can give you just a couple of pointers to more or less help things out along the way. So our first slide kind of sums everything up in just a handful of words. When it comes to talking about weather, there's one thing that's more important than anything else, and that is the sun, because the sun is really responsible in one form or another for all weather that we know here on Earth. Obviously, the sun is responsible for the cycle of heat and cold that we have. Here in the daytime, when the sun's out, it warms up, and at night, when the sun goes away, it begins to cool down. But there's so much more to it than that. The sun's responsible for pressure patterns, for movement of air and wind currents. It's responsible for driving the water cycle. It's responsible for the creation of some of the biggest storms that can occur on Earth. So if we didn't have the sun, we wouldn't have weather as we know it. Now, when it comes to the sun, obviously the most important thing the sun can do. But you may find it surprising to note that the sun does not heat the air. And when I tell students about this and other teachers, I'll say the sun doesn't heat the air. The sun heats the earth. So let's take a look at that a little closer here and see exactly what we're talking about. It turns out that the sun is actually radiating every aspect of the electromagnetic spectrum. And when I talk about an electromagnetic spectrum, I'm talking about X-rays and gamma rays and microwaves and visible light and infrared heat radiation. Any kind of radiation you can possibly imagine, every bit of it comes from the sun. But it turns out that the majority of the radiation that comes from the sun falls into what's known as shortwave incoming solar radiation. Those are things like the X-rays, but most of it is actually concentrated in the visible light spectrum. And if you've ever paid attention to what goes on in your car on a nice sunny day, you've got your windows rolled up, you can't hear what's going on outside you. The sun's energy passes right through those windows as if the window was down. The light passes through, correct? But what happens inside your car? It starts to warm up, right? Well, that's exactly what happens with our atmosphere. We like to say that the atmosphere, for all practical purposes, is transparent to incoming solar radiation. So the sun doesn't do a good job of warming the air at all. Instead, what happens, the sun's radiation passes straight down to the surface of the earth where it's absorbed. And whenever we teach this, we have to teach things like the laws of radiation. Now, you wouldn't do that for 4th and 5th and 6th graders. But for us, as we talk here, one of the laws of radiation says that a good absorber is also a good emitter. In other words, since the Earth is absorbing all of this radiation from the sun, the Earth is going to turn around and emit its own type of radiation. We call it terrestrial radiation, but really it's just sensible heat. So the idea is pretty simple. The sun sends its rays of energy through the atmosphere towards the Earth's surface, where the Earth receives it and then sends it back as heat radiation. But it turns out that the Earth doesn't heat evenly all the way across the board. And that's because the Earth is round. You may remember a guy named Christopher Columbus and some talk about this thing with the Earth being flat and somebody else saying, no, this thing is round. Well, it's a good thing it's round because nobody fell off when they were sailing across the ocean. But at the same time, it's also very important because what is happening here, this is allowing the sun's radiation to reach the Earth at different angles. So, Ms. Marissa, if you'll take me to my next slide, I can kind of explain more what I'm talking about. What is really key to incoming solar radiation is the angle that it's received. If the sun is directly overhead, like it is at midday, that's when you're getting the most radiation. But when the sun is at a low angle, like it is first thing in the morning or late afternoon, you've noticed it's not as hot at those times. That's because the incoming radiation coming in at a larger angle, or at a smaller angle, that is, turns out that it's not as intense. So this is kind of what it looks like. And we're going to place the middle part of the sun directly over the equator. Now, you're probably wondering why all of these rays come in parallel to each other. That's pretty simple, too, because when you compare the size of the Earth is tiny in comparison to the magnitude and size of the sun. So for all practical purposes, incoming solar radiation comes in as parallel rays of radiation. But because the Earth is curved, it strikes it at different angles. At the equator, it's completely vertical, or 90 degrees. At the tropics, it drops off by 23.5 degrees. And drops off even more up towards the Arctic Circle and down at the Antarctic Circle. So basically what happens, the areas getting the most direct radiation are right there at the equator. They're going to get hottest. Areas up near the North Pole and down near the South Pole, well, the sun's coming in at an angle, and they're not getting as warm. Now, I hope as you guys are listening to me, you're thinking about that magical word that the children are going to ask, and that word would be wise. Why? But it would not be wise to answer that right now because I would run out of time with other stuff. So we'll talk more about that in a moment. But it turns out that the sun doesn't always strike directly over the equator. And that's because the Earth is not straight up and down. The Earth is actually tilted on its axis. And the tilt on that axis is exactly 23.5 degrees. That's how we come up with the Tropic of Cancer and the Tropic of Capricorn at 23.5 degrees north and south latitude. So I'm giving you an example of the first day of summer, and notice the northern hemisphere is tilted towards the sun. That means the northern hemisphere is getting the most direct solar radiation, hence it's warmer. So when it's summertime in the northern hemisphere, look down in the southern hemisphere. The sun angle, even at the Tropic of Capricorn, is fairly low. So while those areas may be warm, they're not as warm as they could be. And then 6 months later, everything is reversed. So let's go ahead and reverse things to kind of more or less demonstrate what we're talking about here. And on the first day of winter, I believe we'll be able to get to that next slide. On the first day of winter, it turns out that the sun angle is directly over the southern hemisphere and coming in at a lower angle up in the northern hemisphere. Now, you've probably seen those diagrams where I showed you that straight up and down on its axis, then one way and then another. Well, don't get confused, and that axis is going to work that. That doesn't. The Earth's tilt axis remains continuously, but the Earth has a couple of movements and is and to rotate on its axis. That's why we get night and day. You turn away from the sun towards the sun. But the other thing, the movement of the Earth, is called revolution, and that's the Earth revolving around the sun. So because of that, take a look at winter. Do you see how the northern is tilted away from the axis of solar? However, continue our path, we're going to be counterclockwise into spring. Now the sun is directly over the equal day and equal night. And as we carry on another 3 months in the summer, because of that tilt, the northern hemisphere tilted towards the sun. And this continues in 365-day cycles, and in the end, seasons. So it's called uneven, correct? It's not heating either northern and southern areas or cooler areas toward hotter. Then the part that is near the middle shifts because of the tilt on the axis. But the sort of uneven heating is what's being at the Earth's surface. There are places on the Earth that get the of incoming solar, but they don't the same. What I'm talking about here is the way that land water is going up. So as a little closer look at of heat and water, we're going to that actually and heats up faster and temperatures than water does. So I've given you a nice little where I've got the ocean near. A perfect example is if you've ever been to the and you don't have your boots on, you're walking around on a sunny.
Well, everyone, can you hear me? I think we lost Mr. Jason. So give me 1 second. It's just I think we've lost Jason. So we will. I think he's going to come in here in a second and pick things right up where he stopped. Give me 1 second. You guys can hear me, yes? Laura, you can hear me, and Diane, you can hear me. Okay, let me. Give me 1 second. I'm going to go get him.
Did you guys decide you didn't want to talk to me anymore? Was that what was happening here? At any rate, sorry about that. It turns out that the computer that I was on decided that it was going to kind of go to sleep on me for some reason or another. I guess my presentation was a little on the boring side. So we'll see if we can put it back together. I was talking about the fact that if you walk on the beach, the sand gets hot, but as you head towards the ocean, things begin to cool off a little bit. Can you share my screen for me? I want to take you guys straight to our slides here. And you're not going to be able to see me anymore. We're going to have to stay on the slides, but that'll be okay. So I'm going down here and click on share. However, if you're walking across the beach during the nighttime, chances are that sand is going to be nice and cool. And you put your feet in the ocean waters, and they may feel kind of warm to you. So land and water are all going to be heating up differently. So that is one of the things we talk about. Now, Miss Marissa, how can I change my slides? I have to move my mouse over here and click on this?
Click the side and click it again.
All right. So, because of all of this talk of uneven heating of the earth, because of latitude and because of season and because of land and because of water, we end up with differences in pressure patterns showing up around the earth. So, let me see if I can get us back on the slide here. You guys looking at the slide, are you? My apologies. Now you're looking at the slide there. So the uneven heating of the Earth's surface causes an uneven distribution of pressure. And that is more or less shown on this particular weather map for us. But what I want to show you is that when it comes to pressure, pressure is very important for many reasons. Whenever we start talking about what's happening with, and I'm having trouble here. I'm going to try that. All right, I'm not good at talking and driving at the same time. Areas of the Earth's surface where it gets cooler tend to have higher pressure, and areas that get warmer tend to have lower pressure. And as we talked about, the sun, it can determine the pressure patterns around the Earth. Well, pressure patterns determine the movement of the air. Moving air is what we call wind, and it turns out that air tends to move from areas of high pressure to areas of low pressure. So as you're giving your lessons on weather to your students, one of the things that you're going to be teaching on, they'll be tested on, is the difference between high and low pressure. Well, in high pressure, that's that cooler air we talked about. Cool air is very heavy, it's very dense, so it tends to sink. And when it reaches the Earth, it tends to spread out. So we talk about the air diverging in high pressure. However, in areas of low pressure, the air actually is rising because that's the area that's a little hotter. You've probably heard that hot air or warm air tends to rise. So the air actually comes together and converges in low pressure and then begins to rise. So the way we break it down is we put H's and L's on our weather map. The H you would probably think stands for high pressure. Well, the truth of the matter is it does, but for students we like to say that it stands for happy weather because when the air is sinking, we usually have clear skies and nice calm conditions, so high pressure goes along with dry weather, cool nights, but fairly mild days. On the other hand, the L in low pressure can mean lousy weather because the rising air currents turn out to produce cloudy skies and many times windy conditions because remember the air is moving from high to low pressure. So the low pressure is more or less the receiver of all the incoming airflow, and it can get windy when low pressure is nearby. And consequently, because of the clouds, we can end up with wet weather and stormy conditions. So when we put it all together on a weather map, it might look like this. You've got areas of cold air, you've got warmer air. And notice that we've got to put high pressure near the colder air, low pressure near the warmer air. And separating those are these nice little colored lines. One is blue with triangles, one is red with semicircles. Well, we call these things fronts. And to kind of break it down for you, the definition of a front is just that. It is the front side of an advancing air mass. So if cold air is moving in, well, the leading edge of that cold air is going to be a cold front. And as warmer air begins to move in, the leading edge of that is going to be a warm front. So here's a closer look at cold fronts and warm fronts. And one of the things I want to point out is right here. Cold fronts tend to move faster than warm fronts do. And the reason for that is cold air is more dense. It's heavier. It's like the big bully on the playground. That's a good way to present this to your students. And because of that, because it's the big guy, it can force its way in. Remember, with a cold front, you have cold air that's trying to move into an area that's warmer. And because cold fronts move more rapidly, they tend to produce very rapid ascent of the air in advance of them. Hence, you see these thunderstorms beginning to develop. So your showers and thunderstorms and the most active weather are associated with cold fronts. Warm fronts, on the other hand, the warm air is not as dense, and it has a hard time pushing cold air out of the way. So since it can't push the dense cold air out of the way, it tends to push up and over the cold air. And this causes condensation to take place and clouds will form. And you'll end up with a day much like the day we have today. As you'll see, you've got cold air at the surface and this gray cloud deck moving overhead with little bands of rain hanging out. And believe it or not, warmer air is just off to the southwest of us. It's trying to get in here. It's just having a hard time pushing our cold air out of the way. Remember, the cold air, it's kind of like the big bully on the playground. So here's the kind of idea of what happens when a cold front moves through. We have the cold front pushing into Texas on Monday. And ahead of the cold front, temperatures are 70s and 80s. They're nice and warm. However, by Tuesday, that fast-moving cold front is halfway through our largest state. And behind the cold front, temperatures are beginning to cool off. And as the front continues its progression towards the coast, the entire state has cooled by Wednesday. But not only do cold fronts change the temperature, remember there's that lift along a cold front. Cold fronts produce the most active weather. So near the cold front on Monday, West Texas has thunderstorms. By Tuesday, you have the thunderstorms in the central part of the state. And by the time we get into Wednesday, we should be watching the thunderstorms move off towards the coast. And the thunderstorms, indeed, are out in that direction. So that's the whole idea between cold fronts and warm fronts. Now, we talked also about how the sun can influence the water cycle. Well, first we need to talk about just why the water cycle is so cool and why it does what it does. And that has everything to do with water and what it is able to do. Water is the only substance on Earth that can exist naturally in all three physical states of matter. It can be a solid, which we know is ice or snow. It can be liquid, raindrops or flowing water in rivers, streams, and oceans. Or it can be a gas, which of course is water vapor. And you need all three of these for the water cycle to work. And it turns out, given the pressure and the temperature that we have here at the Earth's surface, that water is the only substance that manages to exist in all of those states, and that's how the water cycle has come to be. We have the evaporation from the oceans and the lakes and the streams, which takes liquid water and puts water vapor into the air. But another thing of interest to talk to your students about is that the plants do a very good job of putting water vapor in the air as well, because the roots of the plants grow down into the ground where they tap the groundwater. And then as the plants get warm, they kind of do what we as humans do. They sweat. But we don't call it perspiration, which is what humans do. We call it transpiration. And that's another good way of getting water vapor into the air. So as this water vapor is in the air and it goes higher and higher into the sky, it gets colder. Because remember what warms the air? The Earth does. So near the Earth it'll be warm, but as you go higher in the air away from the Earth, it gets colder. And when it gets colder, condensation takes place, and condensation eventually leads to precipitation, which replenishes the water at the Earth's surface, and the cycle continues, all driven by the sun. And one of the last things that we notice for the TEAC testing is the talk of hurricanes. And students and teachers alike get hurricanes and tornadoes confused a lot. The big difference here is they're both intense areas of low pressure, but one is small, at least in dimension or diameter, and the other is very large. The hurricane is so large we call it the greatest storm on Earth. But depending on where you are on Earth, people call it different things. We're used to hearing the word hurricane, and that's what we refer to storms that approach the United States from the Atlantic or the Pacific Ocean. We call them hurricanes. But for people out in the Indian Ocean, they tend to refer to these storms as cyclones. And honestly, that's exactly what it is. Remember in The Wizard of Oz, Dorothy, her house was picked up by a cyclone. That was a tornado in that case. But really, it's just a area of low pressure. And that's exactly what they refer to these hurricanes as cyclones in the Indian Ocean. Well, out in the western Pacific, as the storms approach the coast of Japan and China, they take on the name of typhoon. They're really all the same thing. It's just what you call them. And because folks down in Australia like to have a little more fun, I guess, than the rest of the world, they call hurricanes Willy Willies. and that's really the truth, I'm telling you. So what does it take to get a hurricane? Well, obviously a hurricane's an area of low pressure. That's why I've got this great big red L drawn in here. And you know what happens with low pressure? We talked about it. The air flows into low pressure, converges. And when the air converges, it rises and creates these towering storms on either side of the low pressure we see here. And then eventually the air kind of gets pushed out aloft at the top. But the key is down here at the bottom. Hurricanes are fueled by warm ocean waters. That's why you don't get hurricanes in the wintertime. You get hurricanes in the summer when the oceans are warmest, because we really need the water temperature to reach about 80 degrees Fahrenheit or higher. Because when the water temperature is at that elevated reading, we tend to get a tremendous amount of evaporation. And really the fuel for a hurricane is warm, moist air. So the warm oceans provide the warm, moist air. That in turn provides all the ingredients that we need for a hurricane. So when we look at the anatomy of a hurricane, there are three things that you'll want to pay attention to. One is the very center of the storm, which is called the eye. Another is right beside the eye. It's the wall of thunderstorms that surround it. And I use the word wall of storms because that's what it is. It's called the eye wall. And then further out, maybe 30 miles, maybe 70 miles, maybe 100 miles, we have these individual bands of thunderstorms known as spiral rain bands. So upon closer inspection, this is what we notice about these various parts of the hurricane. The eye, which is the center of the hurricane, is where the lowest pressure is. Remember, this is just a giant area of low pressure. But it turns out that the winds inside the eye of a hurricane are actually light. You have to actually get away from the center of the hurricane and get into the eye wall where you find the strongest winds and the heaviest rain. And you also find some pretty heavy rain and some pretty strong winds in the spiral rain bands. But many times these things are responsible for producing tornadoes. So when a hurricane comes inland, it can produce a tornado from one of its many or individual type thunderstorms, while the entire conglomeration of all of these storms spinning around the center eye is what we call a hurricane. Remember the question I said students are going to ask you is why? Well, when you start telling them that low pressure has strong winds, and you tell them that a hurricane has stronger winds than any other storm on Earth, but then you tell them that the middle of that storm, the eye, the winds are light, they are bound to ask this question of you. They're going to say, why is that? And this is really a little more complicated than what you should be talking about for this particular grade level, but they're going to want to know, and you probably want to know as well, and it has to come down to this thing called the Coriolis force. Coriolis force is what causes air to flow in a curved direction. So we talked about air moving from high to low pressure. Well, it doesn't just go straight from high to low pressure. It flows out of high pressure in a clockwise fashion and into low pressure counterclockwise. And if you'll see what's happening, where each of these arrows are starting to come together, well, what this represents is convergence. It turns out that the winds are so strong coming into a hurricane that they actually run into each other before they make it to the middle. If these things were coming in straight lines, they would all meet right in the middle there. but because they're coming in at a curve, they're starting to converge just outside the center. So that's what really creates the eye of the hurricane. So with convergence comes rising air, so you get these columns of rising air on either side of the low pressure, and that's where the eye wall is, and you get those big thunderstorms. So if they ask you, you could tell them it's the Coriolis force, and maybe do a little Googling along the way. And the final thing that we'll talk about in our final 5 minutes of the 30 that we have here is weather and climate. Now, this is a very misunderstood term, a couple of misunderstood terms by people all over the world, and especially in our community because we have so many Spanish speakers in our community. And if you turn any Spanish broadcast for the local news, you'll find that they use the words for weather, tiempo, and for climate, clima, interchangeably. And that's very common for Spanish speakers to do so. But in meteorology, weather and climate are two different things. So we like to break this down for you. By definition, weather is the state of the atmosphere at any given time or place. But I didn't write it down like that on the screen for you because we are going to share these slides with you. A better way to think of weather is what's happening right here, right now. And the weather is constantly changing. 3 days ago, the weather right here in Santa Teresa, where I am, was sunny and rather warm. Today, it is cloudy, it is wet, and it is cold. So we had weather one day, we have a different type of weather another day. But if someone were to ask me that doesn't even live here, say, hey, you know, what's the weather usually like during, late January? I want to come visit and watch the Super Bowl from El Paso. I would say, well, you know, normally it's kind of cold, but not real cold. I can remember some years when the end of January was really warm, and I can remember other years when the end of January was really cold. But on average, it's probably about 50 or 55 degrees. It turns out that by definition, climate is the sum total of all weather. It includes averages and extremes, but most people tend to think of climate is average of what's going on. I just like to point out that it can also include the extremes there. So what we like to say is that weather happens in a particular time and place where climate is generally a long-term generalization of what's going on, and many times people think of climate in regional terms as opposed to one specific location. So ask yourself this question: is it news? Is it something that's going on right now? If it is, it's probably weather. Is it history? Is it something I'm going to read about later? Well, if so, it's probably climate. So we say that climate's what you expect, but weather is always what you're going to get there. So that is more or less the better part of the presentation. I had hoped to be able to give you a few little examples from my camera along the way, but as we found out, my camera didn't want to work, so I had to come in here and take over for Miss Marissa. She seems to have it running again back in that area. But if you have any questions, you can jot down our email addresses. They're pretty simple. There are names separated by a dot. We're all at noaa.gov, and we're going to be passing these along to you through email as well. But hopefully we'll have a chance to share a couple of questions right now. So that's my part in talking about, the weather and giving you some basic ideas and maybe a couple of general ways to explain it. So we bring it down to the level of 4th, 5th, and 6th graders out there. But if you have some questions, we would love to hear them. We do have a couple of minutes left with our broadcast. So I'm going to give it back to Miss Marissa here and let her take over. Miss Marissa.
We switched spots, but we're back up and running. Nothing too traumatic. Diane, do you have any questions for us?
Well, not right now. I just have to process that, and we'll see. But thank you very much, Jason. It's going to be real helpful when it's time to teach.
Yeah, he's great. And Laura, did you have questions?
Is that for me, Laura? Yeah, sorry. No, not at this time. We have 3 teachers here. Right now we're talking about the climate and weather. Hi. And what the difference is in Spanish, that is the confusion that goes with the tiempo and clima, and that is. But everything was very nice and good. Good to hear. Thank you. It was nice.
Well, thank you guys for joining us, and I want to let you know we'll provide you with the slides so that you have those to help reiterate all this to your students. And we're also going to set up some YouTube videos to help reinforce the ideas, and those will have activities that you can do in your classroom to, again, reinforce the ideas so tests go perfectly.
Great. Well, thank you very much.
Okay. Thanks, guys. Have a good day. Have a good weekend.
Thank you. You too. Bye-bye.
Bye.